Good evening and welcome to Lowell Observatory's ongoing celebration of the Lowell Discovery Telescope. This year marks the 10th anniversary since the telescope saw first light, which is when we had the majority of instruments, the mirrors on, and got the first images through it. And it's been, gosh, leading up to that was an exciting time, but that was just the tip of the iceberg. Now the last 10 years has been using it for research, which is it's a phenomenal instrument. It's got phenomenal individual instruments on it. And tonight, we're going to talk about some of these instruments, some of the research done, and we're going to focus on stars and research on stars. And we've got really an excellent collection of scientists tonight representing different areas of research, but having to do with stars. We have Dr. Gerard Van Bell, Dr. Catherine Nugent, and Dr. Phil Massey with us tonight. And what we're going to do is have each of our guests speak for a few minutes about their research and their connections with the Lowell Discovery Telescope and individual instruments. And it's really, a remarkable story. And then after that, we'll just kind of have a round robin and open it up for discussion. At any time during the program, you're welcome to send in questions or comments. We might answer some of those during the initial introductions, but certainly the second half of the program we'll get to questions and discussion. So I think it's going to be fun to talk about this and really give us an idea of just how powerful and versatile this telescope is. Talking about stars is a great way of doing that because our scientists use different instruments and you get an idea of different things that we can study. So first of all, tonight, we'll have Dr. Gerard Van Bell talk. Gerard has been at the observatory since 2011, which is really a pretty neat date when you tie it to the Lowell Discovery Telescope, because that's when, there was a lot of early construction before then. That's the year we saw zeroth light, which was kind of the first image, but before it was fully operational. And so Gerard has been here since essentially the beginning of the use of the LDT, and certainly uses other instruments also, like the Navy prototypic optical interferometer. He has a wide history of research before Lowell Observatory, lived and worked overseas, and is one of the world's leaders in interferometry. But tonight he's going to talk us a little bit about how he uses the LDT and for his research. So Gerard, I'll turn it over to you here.
Thanks, Kevin. I really appreciate that. I'm really excited to talk about the Lowell Discovery Telescope because it's really been a game changer here at the observatory. And it's been very exciting to work with and a lot of fun to work with, both in terms of the people I get to work with and then also the technology and the science that it enables. So I'm going to go ahead and share my screen here and show you a few pictures. What I wanted to do was start off by talking about the telescope in general, and then not go on for too long, but then also have a few remarks about some of the specific science that I've done with the LDT, maybe highlight some of its versatility. The observatory is something that came online in 2012, and so here we are 10 years on celebrating it, and it's a large telescope. It's the fifth largest telescope in the continental US. And so it has a main mirror, is what usually defines the size. The interesting number for a big telescope is what's the size of the main mirror here that's collecting light and giving you a chance to see faint things or be able to see things at high resolution. And so it has one that is 4.3 meters in size. So that's about 180 inches across. So it's about, the size of a small swimming pool. And it's basically, I think it's on the order of about 134 tons of moving mass. So it's the industrial approach to science. When you're building a telescope, one of the things that you're really interested in is how to make it competitive. There are other telescopes out there. We're all competing for research dollars. One of the things I really like about astronomy is that contrary to the notion that a lot of people have that we're up in our ivory tower and we're doing science and not really paying attention to the outside world, astronomy is very competitive and it's very entrepreneurial. And so when you have things that you want to do in science, you got to be able to articulate these ideas, and you got to be able to bring to the table when you're proposing to do work and trying to get support for that work, say from NASA or the National Science Foundation. You have to be able to come up with something that is compelling and has a good value proposition for people that may or may not fund you. And it helps if you have very good tools for that. And so the LDT really represents a real feather in our cap at the observatory in making good pitches for good science. And so one of the things that it has this thing called an instrument cube, and we'll talk about that more. So I won't actually go into much detail on that in this slide. It points really well. When you want to see stuff on the sky, you basically say, I want to look over there, and it actually goes there. And you would be surprised how many telescopes don't actually go there, or at least kind of get in the right direction, and then you got to trim things up, and it costs you time. And every minute that you're spending trying to make the telescope actually point where you want it to go is a minute that you're not sitting there with the camera shutter open collecting photons. And so that's a very important, very useful thing. We can run the telescope from wherever. I have colleagues that are running the telescope from France. I can do it from my little home office right here, which is very nice. That was something that has really set in with a vengeance with COVID, of course. But prior to that, it wasn't used so much. So this is an interesting development. The other thing I'll call attention to is we're really flexible with what you can do with tasking the telescope. And even my fellow astronomers may be like, well, what do you mean by that? So, for example, when I go to other facilities, especially national facilities, if I want to change my target list on the fly, that is not allowed. You have to sign, seal, and deliver what you're going to look at for the given night, a week in advance. And so if you have an idea, or if something you see during the night as far as what you're observing wants you to change your observing program, you have a lot of freedom to do that. So this is a very nice thing about LDT, is that you have a lot of flexibility there. And the majority of the time is with the Lowell Observatory. And so this enables really kind of unique studies that you can't do elsewhere because you just don't have enough time. And then finally, the thing I'll call attention to is, we really dice up a night into small partitions where maybe a given astronomer will get even a quarter night of time. And that's very nice because you can be very flexible about how you do your science, as far as if you have a certain sort of science topic that requires just a little bit of time each time. You could do that, and we're very nice like that. The first bullet point I mentioned was the instrument cube. This is the hind end of the telescope here. We're kind of staring at the business end. And what's really neat about this is that this is where all of the instruments are. So the light is basically coming out of the telescope right at you, out of the screen here. And we have this cube that is lumped onto the back end here. And so a cube has 6 faces. One of the faces is actually attached to the telescope itself, but we have 5 leftover faces that you can put stuff on. So the straight through one right here is this thing called the large monolithic imager. Up here on this face of the cube, the top at 12 o'clock position, we have a camera that I've been working on called a speckle camera. Its formal name is Quizzy. Down here on the bottom, we have a thing called a spectrograph. It takes light and splits it up into its colors, and so you can study all the constituent colors of light. And this is called the Devaney. And then over here, I think it is, we have something that does the exact same thing, but in infrared colors of light that are so red that your eyes can't see them. And then over here, I think we have our speedometer. We actually measure the speeds of stars, and that is a surprisingly useful thing, and that's called Express. And so this is what the cube is. We actually have 5 instruments that ride on the back end of the telescope at any given time. So here, like I said, it's a kind of a Swiss Army knife approach, this instrument cube. We got LMI, we have the Knight's spectrometer, the Devaney, and then these visitor instruments such as the Quizzy instrument that I have, and Express as well. So we can change things on and off. It's very flexible. Again, competitive advantage. We can switch between these very quickly too. So, if on a given night you want to look at an asteroid, you want to get visible light spectroscopy, but then flip a mirror and see what it looks like the near infrared as well, you can do that. It's very easy to do. So that's nice. However, 10 years ago, in the beginning, there was only one instrument. There was LMI, and all those instrument ports were empty because we had just turned the telescope on. And so what does one do with that? And this is, again, highlights some of the niceness of having your own telescope. The LDT is something that the observatory owns, and so we can do what we want with it. We were able to bring visitor instruments there. And this is what it looks like actually when a visitor instrument shows up. We lift it up with the crane, and you can bolt stuff on the back end. And there is one feature of the telescope that is nice. It's got a big mirror, so not only can you see faint things with LMI, you can actually see a lot of detail if you can beat the seeing, if you can basically do better than what the atmosphere lets you do in terms of seeing detail in the sky. And so this is why I saw an opportunity to do some of my own research, where we brought a visitor instrument to lump onto one of these empty ports, and we were able to start getting a different kind of data than just LMI. Sorry, Phil, this LMI was the instrument that Phil was the principal investigator for, is the principal investigator for. And so what was nice was that we had a ability to just bring a new instrument in from a visitor and glue it on there. And we got interesting new data, this thing called DISI, that lets us look at very, very high detail on things in the sky. And so what we did is we started a survey, again, making use of all this time that we have. And one of the things that's very interesting that I've been looking into is for stars that are smaller than the sun, maybe half the size of the sun, all the way down to 1/10 the size of the sun. What is the likelihood that they have an even smaller second star right next to them? And here's an example of some of these nearby stars that we looked at. And so that's the bright spot in the middle. And then you can just see the little arrows here that point out an even fainter little spot next to it. So for our sun, stars like our sun, about half of the stars like our sun have a second star nearby, rather than just planets like our own solar system. For lower mass stars, it's about 1/3, but it's not very well known. So we've had this survey to try and get to know that better and better. We have even built a new instrument to look into that further. So this is the Quizy instrument that we have testing on a smaller telescope before we took it to the big telescope. And we whimsically named this survey the Pokemon survey, where we basically, since again, we have really good pointing, we can look at things rapidly, and we can look at things over a long period of time because we have all this observing time, called this the Pokemon survey, where we tried to look at all of these very, very small stars in the nearby neighborhood to the sun, and see if they had little companions like this guy right here. You know, the idea is you got to catch them all, you got to figure it out. And so of the roughly 1,100 stars in the immediate neighborhood of the sun, it was already known that about 250 of them had a little companion like this. But our survey, using all this time we have in the telescope and using the big collecting aperture of the telescope, which had not been available before for this kind of survey, found almost 30 more companions. So that's all these red spots in this survey here. And so that represents about a 10% increase in the known little companions that are there. And that has all sorts of implications on how do stars form? What if they have planets? Are they likely to have planets? And so this has been a nice feature of being able to use all these strengths of the telescope in concert. I wanted to wrap up with a remark on how the amount of scientific output from the LDT has been really ramping up for the past 10 years. On the left side here, I made a little plot of the number of papers versus the year. It has an interesting feature here where it's going up, 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 and then it takes a bit of a dip. That's COVID. But then apparently in 2021, we're all at home working on papers because of COVID. So there's this big spike right here. And 2022 is still unfolding. So we will see where this lies when we get to the end of the year and how many papers get published using LDT data. It's about a paper every week and a half right now coming off the observatory. And the same thing for citations here. This is another metric astronomers use, is not only can you get a paper out there, can you get your other astronomers to talk about it? And so citations are an important thing to track. And you can see, you know, come about 2018 or 2019, the papers that are out there have 700, 800 citations. And the numbers for later year papers take a while to come up. You know, papers sometimes need to be 3, 4, 5 years old to really get talked about. And so you can see these numbers going up. And, you know, so not only are we outputting science, it's making an impact because people are out there chatting about it. So that's a good thing. With that, I'm going to turn the floor back over to Kevin, and we can move on to our next speaker.
Okay, thanks so much, Gerard. And we'll talk a little bit more about your what you've shared with us. There is one question that now's a good time to ask. The question is, why did you call it Pokemon Speckle Survey? What's Pokemon referred to and Speckle?
Yes, so speckle refers to the technique when you look at something at very high resolution through the atmosphere kind of mushes out what you're seeing. And so it doesn't give you kind of a bright single star. It gives you like all these little bright spots that are kind of spread across the focal plane. And each one of those bright spots is called a speckle. And so that's why the technique is called that. You look at all the speckles at once really fast, and with the right math, you can peel it apart and get the image back as if there was no atmosphere there. And then we call it Pokemon because we are astronomers and we like really creative acronyms. And in this case, this was the pervasive overview of companions, with a K, of every M dwarf, low mass star, in our neighborhood. So that's Pokemon. It is not too tortured of an acronym. So we've had a lot of fun with that. And the best part, of course, is all the product tie-in that you can get with the survey now. So
that's great. Thanks so much. And we'll get back to some of your research a little bit later. Next, we're going to hear from Dr. Catherine Nugent. Catherine is affiliated with the University of Toronto, as well as Lowell Observatory, and first was affiliated with the observatory back in 2008 as an undergraduate, and she came back. And she kept coming back, and she's still affiliated with us, and it's been a really great run. Catherine, you started before Gerard was even here, actually, as an undergraduate, and you've seen LDT grow, and also have been able to use it for different kind of research, still stars, but different kind of research using different instruments. So let me turn it over to you, and you can talk a little bit about your connection with the LDT.
Yeah, definitely. Thanks so much. Yeah, I came back when I was an undergrad, came back again as an undergrad, came after undergrad, came after grad school. I just keep showing up back at Lowell. And so my research focuses on kind of the opposite type of stars that Gerard just talked about and does research on. I look at the massive stars, so stars that are many times bigger than our sun. And so I am also going to share a few slides. So the stars that I have been using the LDT to study are called red supergiants. So these are evolved massive stars that start out their lives as 8 to up to 30 times the mass of the sun. They burn through hydrogen, they start burning through helium, and they expand. And as they expand, they turn very cool and they start to look very red or orange. And one of kind of our favorite red supergiants that many of us know and love is Betelgeuse. And so this is a picture I took out at Anderson Mesa, one of the other observing sites where Enpoy is that Gerard was talking about. And this is the Orion constellation. And if you look in the armpit of Orion, you see Betelgeuse. And so this is a red supergiant. And just to kind of underscore how large these stars are, this is a comparison of how the sun would compare size-wise to one of these red supergiants. And so if you put it where the sun is in our solar system, it would expand out well past the Earth out to Jupiter or Saturn. And so they are very large stars. And to kind of put this in context with the stars that Gerard was talking about and studies, this is called a Hertzsprung-Russell diagram, where you have temperature on the x-axis and luminosity or brightness on the y-axis. And so the sun is going to be at around, I don't know if you can see my pointer, but it's sweet. Okay, so the sun is around here. The stars that Gerard is talking about are more down to this side, and red supergiants are way up here. So they are very cool and they are very luminous. So they are very bright. And if they are in our own galaxy, they are some of the brightest stars, such as Betelgeuse, if they're kind of close enough by. And so I have been studying these stars for the past couple of years, And as Gerard talked about, I have also been interested in how many of them have companions. And so how many of them have some other type of star that kind of either orbits around them or orbits with them. And one of the things that I have been using the LDT to learn is kind of how do these red supergiants interact with their companions, and how does kind of the evolution of, if you have a red supergiant next to a companion, how does it kind of evolve over time? Are they very close together? Are they interacting? Or does something else happen? And so to kind of show how some of these interactions might occur, I have some pictures of animals to kind of help us with this. And so I have my dog Meg, who is snoring beside me on the couch, playing the role of the red supergiant, and then my previous kitty Marlo playing the role of the companion. And so if you kind of start out with these two stars, they might be kind of separated and not really interacting. You know, you can see that these animals in this case aren't really paying much attention to each other. They're kind of orbiting around each other. But over time, as many different things could happen, the red supergiant could kind of expand, or just kind of the orbits could become perturbed. And over time, they grow closer together, and you'd start to see a bit more interaction. And so in this case, you can see the companion star is kind of accreting material. It's grabbing material from its companion red supergiant, and the red supergiant is starting to maybe notice that it has a companion, and so you start to get this interaction. And if kind of the interaction continues, or the red supergiant continues to expand, then in some cases you'll get the red supergiant will actually consume the companion. And so you'll be left with the companion cat or star has been sucked into the kind of central red supergiant, and you'll get what's called a merger. And so what you see when you just look at these stars is what appears to be a single red supergiant, but it's possible that at some point in the past, it actually merged with a companion. And so I have been using the LDT to try and figure out if the red supergiants we see in the night sky are actually merger products, if previously they had a companion that has been kind of consumed by them. And so one of the instruments that Gerard mentioned is Express, and kind of the speedometer one, the one where we're trying to figure out very precisely kind of how fast these stars move. And so I haven't been using it quite for that way, but I've been using it to try and characterize these massive stars in another way. And so this is the extreme precision spectrometer, or Express, and it gives us a lot of information. And so on the top, we have a spectrum of a red supergiant in our own galaxy. And you can see that there's all of this stuff. There's all of these black lines. And the exciting part about Express is that you might think like, oh, it looks really noisy. Like, why is all that stuff there? But all of that stuff is information that we can use to learn more about these stars. And so with this, this plot, we have wavelength on the x-axis and flux or brightness on the y-axis. And if you zoom in, if you just kind of take this little area of the upper plot and then look in more detail, you get the bottom plot, and you see that all of these lines, these kind of vertical lines, they tell you about the metal content of these stars. And so here on the bottom, I show this nice iron line. And so we can use all of this information to try and figure out if the red supergiants and other stars that we see in the night sky used to have companions and have since merged, or if they are currently single, or even if they have a companion now. And so by figuring out stuff about the strength about all of these lines, about their width, kind of all of these different properties, looking at this spectra, we can better understand kind of the history of these stars and what might happen to them in the future. And so I have been observing with Express a bunch of the red supergiants in our own galaxy, and now in the process of trying to use this spectra to better understand the red supergiants. And so that's what I have been using the LDT for. And I will stop sharing. Oh, Kevin, I believe you're muted.
Thanks, Catherine. I really appreciate your display there with your dogs and cats. I've not seen that before. That's excellent. I was wondering how long it took to get that picture of your dog with his tongue out.
It was a complete accident, actually. And it wasn't until we were just trying to get at least one picture of the two of them together. And we ended up taking like 50. And when we went back and looked, it was like, oh, this is perfect.
Well, it's a great educational tool. Thanks for sharing that.
Definitely.
Well, our last speaker, certainly not least, Dr. Phil Massey, has been at Lowell Observatory for pretty much the 21st century, for as long as it is. And, you know, Gerard kind of lobbed a softball here to set it up. He was talking about different instruments with the LDT and talked about LMI. And LMI is, I think, an instrument that most people can understand because it's a big camera. And when I say big camera, it's a big camera. And Phil's going to talk about why I say that and some of the research he's done with it. And I also will mention that Phil, besides or kind of connected to the great research he's done, he and Catherine and others on the team have generated some spectacular images that are available from our website. And it kind of gives you a visual idea of the quality of what LDT can do. Sometimes when you see the numbers and graphs, you need a little explanation, but just seeing these images really captures the imagination. So Phil, let me turn it over to you, and you can correct anything that Gerard and Catherine said, because you have the benefit of going last.
I wouldn't do that. Thank you, Kevin. So let me start off here. Okay. So I got involved in the LDT. We had been talking about the next generation Lowell telescope for long before I got to Lowell. And by the time I came on board, it was pretty well defined. It was going to be a 4-meter class telescope. And how the birth of LMI took place at a meeting where Dr. Bob Nellis, who was director of the observatory at the time, was talking about how we needed a camera. And my wife is the astronomer, Deidre Hunter, and she is very interested in how stars form in galaxies. And she has been pushing how faint you can see around small irregular galaxies. And perhaps at some point she'll be on one of these and talk about her research. I'm not going to go into that right now, except to say that I was strongly motivated to, for any camera we have, to be able to do the work that she needed to do, which involved being able to measure down to very low surface brightnesses. And the way that CCDs were made large in those days was you would take 6 or 8 of them and you would sort of glue them together, but there would be gaps in between them. They would be mosaic cameras. And now they have mosaic cameras of hundreds of CCDs. But, and I was proposing at this meeting that we build a similar camera to what we had at Kitt Peak. And Bob Nellis said, no, we need to do something better than that. And he had heard that they had just made a giant single CCD, one that was the same size as putting 8 large CCDs together, but didn't have any gaps between them. And it was clear to him, he had the vision that that was the direction we should go. And I quickly got on board on that because it was clear that Deidre would be able to do her project much, much better using that than using a mosaic. And we applied to the National Science Foundation for several years. I would write proposals and we would be turned down. But eventually they said yes, and they were kind enough to give us a bunch of money for building what was then really the largest single chip CCD that you could build. And here is a picture of the chip compared to the size of a penny. And physically, it's about this big. And here is a picture of the camera on the telescope. And Dr. Ted Dunham, who was the instrument scientist who led the building of the LMI, even though I'm the PI for the instrument, I actually didn't do anything other than write the proposal and talk about what science we were going to do and think a little bit about how we would reduce the data and the like. But we're sitting at the telescope, trying it out on the sky for the first time, and Ted said, "We need to take a pretty picture." And so we took some ultraviolet, blue, and red images of this galaxy, NGC 891, and I contacted my good friend and colleague, Dr. Catherine Nugent, and said, "Could you make this into a pretty picture?" And thus the Oh My Gallery was born. We did this with the first light image. These are a couple of my favorites. This is the Helix Nebula, and then one of my favorites, the Horsehead Nebula. And we'll show you another one in a few minutes. But now I'll talk about the science. So Deidre's been having a great time during her science with it. And Catherine has described the science that she's been doing with Express. But now I'm going to tell you about some science that Catherine and I have been doing with LMI for our own work. And this involves then talking about Wolf-Rayet stars. And Wolf-Rayet stars are extremely massive stars, even more massive than the stars that Catherine was talking about. These are the ones that are evolved massive stars that are above 30 solar masses, at least their progenitors were. And Wolf-Rayet stars were, the term began because of these two gentlemen, George Rene and Charles Wolf, who in 1867 were using a little visual spectrometer on a telescope located in downtown Paris. And usually when you look at the spectrum of a star, when you take the light from a star and break it up into its colors, you see something like this. Catherine showed some beautiful examples of this from Express. And what you see is a colored continuum, but superimposed on that are dark bands where light has been removed. And these are the lines that are going down. If you were to make a plot, this plot here shows the flux, which is how bright something is, against the color from blue over on the left to red on the right. And that's how most stars look. But what they did, what they found, what Wolf and Rayet found, were 3 stars, all within a degree of each other in the constellation of Cygnus, who instead had these big, bright, strong emission lines, lines that were brighter rather than dimmer. And this is an example of the spectrum of one of these Wolf-Rayet stars. And what Wolf-Rayet stars are, it can be likened to peeling an onion, in which you have a star and it has a hydrogen-rich outer layer. And meanwhile, in the core, you're converting hydrogen to helium. And so down below the hydrogen layer, you have some helium and nitrogen. And if you peel off some of the outer layers, you expose the helium and nitrogen. And those were the lines we see here. These emission lines are due to helium and nitrogen in that one. And if you continue peeling the onion, you eventually get the products of helium burning, which are carbon and oxygen. And that's a different type of Wolf-Rayet star. And if you were to take a small section of the spectrum and blow it up, as I have here over the right, it gives you a clue of how you might go looking for these. And you could, what we have done is we've designed a filter system where we have one filter that is centered on the strongest line in the WC, the Coben type Wolf-Rayet stars, a filter that's centered on one of the strong nitrogen lines in one of these stars, and one that's on the continuum. And so rather than taking spectra of 100,000 stars in a nearby galaxy, we can take an image that shows 100,000 stars, but through each of these three filters. And when we do this, and this is from a paper that Catherine and I did a few years ago, in which we were looking for Wolf-Rayet stars in the Magellan Clouds in the southern hemisphere, not using the LDT, but a telescope that I'll shortly describe. If you take one of these online bands and subtract the continuum, well, the Wolf-Rayet stars just pop out as these bright objects. And here we are. We decided to go looking for Wolf-Rayet stars in the Large Magellan Cloud. This is what this little galaxy is here. You can see this galaxy. It's only 50,000 light years away, and you can see it with your bare eye. You go out on the dark night. And this is the SWOLP telescope, the 1 meter telescope, and this is a southern Milky Way. This is probably one of the things that I regret most about not being able to travel for the last 2 years, is we would be able to go down to northern Chile a couple of times a year and use these remarkable facilities. And so Catherine and I and our collaborator Nydia Morale decided to go looking for Wolf-Rayet stars in the Magellan Clouds so that we would be able to compare their numbers to stars like the red supergiants that Catherine described. And once we found candidates, after subtracting them, we go over to the big telescope, one of the Magellan 6.5 meters, and take spectra of the stars that we thought we were Wolf-Rayet stars to see if we saw these characteristic emission lines or not. And it's always the exciting thing in science is not just when you successfully find the things you're looking for, but when you find the things you weren't expecting to find. And what we discovered was a new type of Wolf-Rayet star that had never been seen in the 150 years that Wolf-Rayet stars have been known. And this type of Wolf-Rayet star not only had the emission lines, but it had these absorption lines as well. It was sort of what we think is a transition object. This is actually what Catherine did her master's thesis on here at NAU and Lowell 6 years ago now, roughly. So we don't understand how these stars form exactly. And we don't know of any of them in the Milky Way. And so Catherine pointed out that really the way we could solve why we see them in the Magellan Clouds, where we don't have as many heavier elements as we do in the Milky Way, was to go to the LDT and take images with LMI of this galaxy here, M33. And M33 is a very nearby galaxy. It's only a million parsecs away. And it is nice for this project because the concentration of heavy elements is greater in the center of M33 than it is in the outer region. And so our thinking was that if we found this new type of Wolf-Rayet star in the outer regions, but not in the inner regions, it would tell us that metallicity, we refer to metallicity as how much of these heavier elements are around. It would tell us what range of metallicities they formed over. And so we got, LMI is a large camera and you need really big filters. And so we got a filter set made for LMI that were centered on the two emission lines and continuum. And we took images of M33 as shown here in another one of the images that Catherine turned into a really nice color image. And when we found candidates, we then went to the Gemini 8 meter telescope on Mauna Kea to take spectra of the stars that we thought were these new type of Wolf-Rayet stars. Indeed, we found 30 candidates. And we're still in the process of reducing those data and analyzing them. But here's our most promising one. And it has the same characteristic emission line and these emission lines. The signal to noise isn't good enough to see the absorption line. But one of the things that distinguished these other Wolf-Rayet stars we found was that they were faint. And this star is fainter than the other Wolf-Rayet stars in M33 by the right amount. And so this is just a little reminder. We see the same region of the spectrum here, and that's what happens, the difference between having a nearby one of these stars and one that's very far away. So that's the work that we're currently doing. And let me stop sharing, and we can then all talk about, answer questions that people have. Back to you, Kevin.
Well, that's great, Phil. Thanks for explaining that. And again, the LMI is an instrument that not only allows spectacular science, but allows our casual visitor who doesn't have a background in astronomy kind of a feel for just how powerful the telescope is and the instrument. You mentioned a couple of things. First of all, you mentioned Bob Millis, and he's certainly we could do a lot of programs on Bob Millis, our longtime astronomer and director. And he's the one, I believe, the first nicknamed the LDT, the Swiss Army knife of telescopes, because of its versatility. And we're getting an idea of this as we talk tonight. I also wanted to ask Phil one clarification. You mentioned M33 is about 1 million parsecs, I think. Maybe just define what that means. What's a parsec, and how far is that?
So a parsec is about equivalent to 3 light years. And so why we call them parsecs, it has to do with holding your finger near your face and opening one eye and then opening the other eye. Your finger shifts relative to the background. If you move your hand further away and do this, your finger doesn't shift as much. And so that effect is parallax. And we measured the position of nearby stars. One way of doing it from the ground is by taking an image of a star field at one time of year and then 6 months later. And you have this large baseline of the Earth's orbit. And so we've defined 1 parsec to be the distance at which a star has a parallax of 1 arcsecond, where 1 arcsecond is 1/3600th of a degree.
Okay, that's excellent. Thank you.
You're welcome.
And a couple of questions that are coming in. One is kind of open up to everybody. You've talked about your research with the LDT and the various instruments, looking at different sizes and types of stars. What would your research look like if there was no LDT? Gerard, why don't we start with you, since it's been longest since you spoke?
Yep. So it would be a lot more difficult because you have to then try and get time on other telescopes, sometimes competitively. In fact, the kind of work that I do, there is a similar camera on a slightly smaller telescope in southern Arizona on Kitt Peak, the WIN telescope. And I've actually gotten time on that to kind of supplement what I'm doing at LDT. But there is a lot of demand for that telescope because it's a telescope that's open to the entire US community. And so everybody's asking for a piece of the pie there. And there is some new instrumentation on there that basically has started to kind of edge out the work that I do, because there's enough people asking for time on this other instrument there that I've just stopped even asking. And so, you know, if there was no LDT, it effectively would have ended this line of research that I'm doing right now. And so, yeah, it's a huge leg up on doing the things that I want to do when I want to do them.
Yeah, I can jump in as well. I think one thing that I really enjoy about the LDT is it makes me think about new science that I can do using instruments that I wouldn't regularly use. And so, for example, Express is was not really made to study massive stars at all. Like, it was made to find planets and to learn about stars that probably have planets or something. And so it was fun to kind of think of, well, this is a really cool instrument. Like, I haven't seen a lot of really high spectral resolution data of massive stars in our galaxy, and what could we learn from that? And so the Express, looking at kind of the mergers, all of that really came out of the fact that here is this telescope that I have access to with this really interesting instrument, and what can we learn, and kind of just see what happens. And that's something that again, you don't get at a large telescope, where it's really hard to get time, and you really have to have kind of more background before you apply for time. And so this whole project, I think, really came from having this access at the LDT.
And something you said there echoes a long-standing tradition at Lowell, that the observatory owns our own telescopes. We certainly have science partners, but owning our own telescopes allows for long-range studies of things. It allows, if something happens suddenly, we can divert off to that at short notice. It offers a lot of flexibility, and that goes back really to the beginnings of the observatory with Percival Lowell and his staff way back when. So it's one of the strengths of the observatory that continues today. Phil, what are your thoughts about?
So I love the LDT. That said, if the LDT disappeared tomorrow, it would have some effect on my science. But I think most of us, it's like trying to deal with financial issues. You want to have a diverse portfolio. And so I think most of us use a variety of instruments. Gerard, I know, does a lot of his work out at Endpoint doing interferometry. You can't do interferometry, really, straight interferometry on the LDT, although I guess he would argue all telescopes are interferometers. So I've learned that much from Gerard.
Yes.
And Catherine will shortly have wonderful access to telescopes through her new postdoc position. I do a lot of my research on the Magellan Clouds, which you can't observe from the Northern Hemisphere. But the LDT, that doesn't say that and we do a fair amount of our work using Hubble Space Telescope, which, location, location, location. But the LDT is still very important to my research, in the sense of I have an idea and I can go and do that not a year or a year and a half from now, but I can do that in a couple of months. And if I really want to get an image next week or a spectrum next week, I just have to look on the schedule and say, hey, Gerard, can I have half an hour while you're doing this? And it's also, many of us work with students here. And the ability to be able to take that student out to the telescope and have them do something hands-on is vital for an observational astronomer to learn what they're doing. And that's becoming more and more difficult as telescopes become more Q-oriented. Can't do that with Hubble Space Telescope, and it's very difficult, it's very difficult to take someone to Chile. It's expensive and a long trip. But LDT, it's an hour and a half away. And so I guess that's my answer. It fills a very important niche, but it's not the only niche that most of us are utilizing.
I think something you said there, Phil, really resonates, and that's the connection with students. And Catherine, you're early in your career, but you certainly had mentors here at Lowell Observatory, including Phil. But Phil and Gerard, you both have been mentors to many students through the years. And like we were talking before, there's a certain glow to you right now because you both had students that just recently defended their dissertation and are moving on in their careers. And that's a critical thing that the observatory does, is not just do science, but nurture the next generation of scientists.
Yes. One of the things that the LDT allows an opportunity for as well is my student who just finished up, another Catherine, Dr. Catherine Clark. She helped build this instrument that is on the LDT now, and it's becoming a vanishingly small opportunity for people to get hands-on experience with building instruments, and seeing the data, seeing all the way through to the end of getting data and using it in their thesis. And it's a very powerful thing for nurturing and mentoring that next generation of leaders that is going to build the telescopes and build the spacecraft that give the next great discoveries and show not only are there planets around other stars, but what are the prospects for life on those planets. And it's really important to have people who have the joy and the frustration of building instruments, because it teaches you a lot about what to expect with that kind of work.
Now we're celebrating the 10th anniversary of the LDT, but also there's always looking to the future. At the observatory, Lowell was founded in 1894. We had telescopes. Jump ahead half a century, and those telescopes weren't big enough. We had to get bigger, more state-of-the-art telescopes. And we got what was called the Perkins 72-inch. Jump ahead half a century, if we're going to maintain our position as a world-leading observatory, we had to get better, bigger telescopes and technology. Thus was formed the LDT. What's the future of LDT? What's the expected time span of it? And what do you guys see for the future? Gosh, we don't want to speed up time, but how's it look down the road?
So the LDT in telescope years, kind of like inverse dog years, is still pretty young. And technology is moving fast. But one of the nice things about telescopes is the base function of the telescope is to have a big chunk of glass or some lens in the right shape, and to compact all the photons down to a spot where you can do something with it. And as the technology advances, you can do a lot more and more with that spot, even though the big chunk of glass is still just doing what it did. And so this is why, say, the 5-meter Hale telescope, which initiated work in 1947, I think it was, is still operating every night on Palomar Mountain. And, and we're in the same class of size as that 5-meter Hale telescope. And so I have a great deal of excitement for the future of the LDT, in that, we have ideas on how we want to add new instruments on the back end of the telescope. We have ideas about how we want to make it so that we can have light come out of the two yoke arms, the shoulders of the telescope that hold the main tube of the telescope. That's called a Naismith port. And there are actually already platforms up there. We definitely built the telescope with the future in mind. And on these big platforms, you can put very large instruments, not something that would just fit on a little face of an instrument cube. And you can do very fancy things with tricks of light, and being one of the magicians of light that we are as astronomers. And so there's I think a very exciting future ahead of us for the next decade and 2 decades, and so on and so forth, with the LDT.
We've got a little bit more than 5 minutes left, and we've got a couple more questions. I think we'll kind of turn into the Ask an Astronomer portion of the show, not necessarily LDT. One question from Nicholas: do you any of you plan on getting time on the James Webb telescope? And I think also maybe one of you can answer, just do a comparison between James Webb and LDT and what they're different. If you can compare them a little bit.
Do you want to jump on that, Phil?
Or Catherine?
Hot potato?
So the Webb is really amazing, or it will be amazing. But right now, not much of my work is in the infrared. What I have been using in space is the Hubble Space Telescope, because the Hubble Space Telescope is very good at taking spectra or images in the ultraviolet, the opposite of what the Webb is designed to do. And unfortunately, the Webb will not be able to observe in the ultraviolet. And so when Hubble is gone, that will be a capability that is lost not only to me, but to astronomers around the world. And so that's an issue. The LDT has an advantage over Hubble in that the collecting area is much larger. It's a 4.3 meter telescope. Hubble is only a 2 meter telescope, but Hubble is located in a better place. Certainly, lots of people are very excited about using the James Webb Telescope, including my astronomer wife, who does work in the infrared. So,
okay, let's take. I think we have time for another question. Here's another Ask an Astronomer thing from Adam. Seeing if any of you have insight on the recent micronova discovery and what the nature of that is.
So what I know of that is that there are stars that will, just as Catherine was talking about, will take material from their companions. And in this case, these are even stranger stars called white dwarfs that are basically the left out over cinder of a dead star. But if they have a nearby companion that's dumping material on it, the surface will get a few feet deep in hydrogen, and then it'll ignite like a hydrogen bomb, and it'll go into a nova outburst. It'll actually brighten up, and this will happen every 10 or 20 years with some regularity with some of these periodic novas. What they recently discovered is that some of them appear to have kind of localized explosions just at the poles. And this was discovered by the TESS satellite, which is a satellite in space that is it's a much, much smaller optical system than the Webb or even the Hubble, but it does rapid brightness measurements, and so it can detect things that change in brightness very quickly. And so what's really neat about thinking about this discovery in relation to the LDT is that, if now we know to look for these things and you see one that goes off, you get a little blip in brightness. The LDT is very easy to task, and you can interrupt the queue, you can call up on the phone, you can be like, hey, I got to interrupt here. And you can jump in and try and observe transient events like this that are being discovered by TESS and will be discovered in much more number by the Vera Rubin Observatory that's coming online very shortly. Vera was a good friend of the observatory who passed away recently, and this new observatory that's specifically designed to look for these sort of things will probably give us a lot of alerts in the future.
Okay, great, Gerard. Well, we have time for one more question, kind of a quick answer, and this one's for you, Catherine, from Nicholas. Any prediction on when Betelgeuse will go supernova? Get your crystal ball out.
I wish. Sadly, probably not in the near future. It looks like Betelgeuse has kind of calmed back down. And the idea is that it kind of puffed out kind of a bunch of stuff, kind of gas and dust that blocked the light. And so while there was hope that this eruption was maybe preceding a bigger, more exciting supernova explosion, it looks like Betelgeuse has kind of calmed back down. So as someone who studies massive stars, it would be very exciting if Betelgeuse exploded. But sadly, I don't think that it's going to happen in the next couple of weeks.
Don't hold your breath. Right.
Yeah.
Well,
my standard answer is that it's guaranteed to go supernova sometime between tonight and 100,000 years from now.
Narrowing it down. Well, we are out of time now, so I'd like to thank Dr. Nugent, Dr. Massey, and Dr. Van Belt for joining us tonight. The LDT is a powerful telescope and allows you and our other scientists and our partner scientists to do so much research. And we really appreciate you taking the time tonight to talk about that, because again, mission of Lowell Observatory is not just to carry out the science, but to communicate that science. And it's important to do that to inspire future generations and to build a more literate society about the universe around us. So thanks for joining us. Thanks to Heather Craig for doing all the behind the scenes stuff tonight.
Yay.
And making everybody look good. And thank everybody for joining us. So have a great night, and we'll see you next month as we continue celebrating the Lowell Discovery Telescope.
Thank you, Kevin.
Thanks very much.